In this section, we're going to be looking at the reaction quotient. And before we go any further with this, I want you to remember what the reaction quotient is. The reaction quotient, we use the letter Q to indicate reaction quotient, and I want you to be quite familiar with what that quantity is. The reaction quotient gives us the same ratio as the equilibrium constant expression, but for a system that is not necessarily at equilibrium. So we'll find that there are all kinds of examples where we might want to use this, but let me show you how this works. So here we've got an equilibrium reaction. This is just a generic one where the lowercase letters are the coefficients and the uppercase letters are the chemicals. So the equilibrium or the reaction quotient just looks exactly like the equilibrium constant expression, except that these quantities are not necessarily at equilibrium. The value of Q by itself is not that great. It's only when we take Q and compare it to the equilibrium constant K that we can get some real information about where our reaction is relative to equilibrium. So when we compare Q to K, first off, if Q is less than K, then the reaction will proceed towards the products. In other words, reactants will get converted into products. The concentration of reactants will decrease, and the concentration of products will increase until Q is equal to K. So again, when Q is less than K, the reaction proceeds to the right. If Q happens to be equal to K, which that can happen, that means that the reaction is at equilibrium. Now, just like with all other equilibrium processes, the forward reaction and the reverse reaction continue to happen. However, we'll find that the forward and the reverse will be, the rate of the forward and the reverse will be equal to each other. So it will be at equilibrium. Finally, if Q is greater than K, then the reaction will proceed towards reactants. In other words, the reaction will shift to the left. The concentration of products will decrease, and the concentration of reactants will increase until Q is equal to K. So that is how we compare Q and K. So now what we want to do is look at an example where we can compare Q to K and see which direction the reaction will shift to get to equilibrium. So we'll look at number 37. So here is number 37, and you'll see that we've got the equilibrium reaction, COCl2, which is in equilibrium with CO and Cl2. We've got the equilibrium constant given to us, and the equilibrium constant expression is going to be the concentration of CO times the concentration of Cl2 divided by the concentration of COCl2. So we've got that expression. So what we're going to do is we're going to take these values and put them into that expression, but in terms of Q. So Q, again, I will rewrite it. So the concentration of CO times the concentration of Cl2 divided by the concentration of COCl2. In this particular scenario, our carbon monoxide is 3.3 times 10 to the negative 6. Cl2 is 6.62 times 10 to the negative 6. And then the concentration of COCl is 2.00 times 10 to the negative 3. And just checking, there's no coefficient, so that means all the exponents are 1. It's always a good idea to check that when you're setting up a problem. So now let's put the numbers in. So 3.3 times 10 to the negative 6 times 6.62 times 10 to the negative 6. And then we'll divide by 2.00 times 10 to the negative 3. And that gives us, it looks like we've got one sig fig, so we're going to call that 1.1 times 10 to the negative 8. So that's Q. All right, so since that's Q, we now need to compare Q to K. You'll see that 10 to the negative 8 is greater than 10 to the negative 10, so Q is greater than KC. Therefore, the reaction will proceed to the right. I'm sorry, if Q is greater than KC, that means the reaction will proceed to the left. That means the reaction will proceed to the left. All right, so for the next part, so we'll do Q is equal to, again, carbon monoxide. So 1.1 times 10 to the negative 7. For chlorine, 2.25 times 10 to the negative 6. And COCl2 is 4.50 times 10 to the negative 2. So now we'll put those numbers in. So 1.1 times 10 to the negative 7 times 2.25 times 10 to the negative 6. And then we'll divide that by 4.50 times 10 to the negative 2. And that gives us a quantity of 5.5 times 10 to the negative 12. Well, 10 to the negative 12 is less than 10 to the negative 10. That means that Q is less than Kc, and so the reaction will proceed to the right. All right. What that means when the reaction proceeds to the right is that the concentration of our reactant will decrease, the concentration of these products will increase, and they will continue to do so until Q is equal to K. All right. For part C, we want to look at this value. So Q is equal to 1.48. 1.48. And let me fix that real quick. Times 10 to the negative 6. And then 1.48 times 10 to the negative 6 for the chlorine as well. So those are both the same value. And then the concentration of COCl2 is 1.00 times 10 to the negative 2. Okay, so now we can do that calculation. 1.48 second EE negative 6 times 1.48 second EE negative 6. All right, and now we will divide by 1.00 times 10 to the negative 2. And that gives us 2.19 times 10 to the negative 10. So times 10 to the negative 10. You'll see that that is equal to Kc. So Q is equal to Kc. Therefore, we are at equilibrium. So that reaction is at equilibrium. So our last concept is Le Châtelier's principle. And the way that Le Châtelier's principle works, I need to switch over to the presentation. The way that Le Châtelier's principle works is this. This is our statement that is in the textbook. I actually modified it a little bit. If you're feeling curious, you can go see how I modified it. But If a system at equilibrium is disturbed by a change in temperature, pressure, or the concentration of one of the components, the system will shift its position so as to counteract the effect of the disturbance. In other words, if we want to talk in terms of Q and K, let's say we've got a reaction that's at equilibrium. In other words, Q is equal to K. And then we come along and do something to it so Q is no longer equal to K. Well, then the reaction is going to shift so that Q gets back to K. And that is how Le Chatelier's principle works. I am going to explain it a little bit differently. I'm going to show you some math to prove that I'm correct. And I'm going to show you an example of the Haber process. Now, this is the process that is talked about in the textbook, but I'm going to show you the Haber process. The Haber process is a very important reaction. It's a reaction where it makes it possible to fix nitrogen. And by fix nitrogen, we mean to take elemental nitrogen that is in the air. Nitrogen makes up 78% of our Earth's atmosphere, and approximately 0% of it is available for biological purposes. So it takes a chemical reaction to convert that nitrogen into something that is useful. So this is the chemical process where N2 plus hydrogen gives us ammonia. When you take that ammonia, there's some other reactions that you can do to it, and with those other reactions, you will get you can convert it into nitrate or into some related compounds, ammonium, whatever. And in the process of doing that, you can end up getting a compound that you could use as fertilizer. This is one of the biggest industrial processes in the world. Approximately 3% of all natural gas on Earth that is produced is used for this process. Approximately 3% of all carbon emissions on planet Earth come from the Haber process. And about 1% of all energy usage goes into doing the Haber process. So this is a very energy intensive process, but what it allows us to do is to produce nitrogen artificially and have fixed nitrogen so we can increase crop yields. Without this process, it is estimated that there would be about 3 billion fewer people living on Earth right now. And I think everybody would agree that would be a much different Earth. Okay, so I've chosen 195 degrees Celsius for a reason. I will warn you that this reaction doesn't work at 195 degrees Celsius. The activation energy is too high. You need a catalyst, but even with the catalyst at 195, it just won't work. But the reason I chose 195 is that at 195 degrees Celsius, it just so happens that the equilibrium constant comes out to 1. So let me write the equilibrium constant expression. Kp is equal to the partial pressure of ammonia squared divided by the partial pressure of nitrogen, and then also divided by the partial pressure of hydrogen cubed. So again, these come from the coefficients in the balanced equation. And as I mentioned, at 195 degrees Celsius, the value of Kp is approximately 1. That makes it easy to do our examples, and that's the only reason I chose this. If you were actually trying to do the Haber process at 195 degrees Celsius, you would have a very long day and you would not produce any ammonia. So just keep that in mind if you're going to start your own ammonia production facility, which you're probably not going to do. So let's start. Again, we're going to start with what I call initial conditions. So we're going to start, again, everything here is going to be at 195 degrees, and then we're going to start at 1 atmosphere of pressure for all of the gases. So nitrogen's at 1 atmosphere, hydrogen's at 1 atmosphere, and ammonia is also at 1 atmosphere. We want to compare the value of Q to K. As you recall, K at 195 is equal to 1. Well, under these initial conditions, if all of these partial pressures are equal to 1, we will get 1 squared divided by 1 divided by 1 cubed. That will give us a value of 1. No calculator needed here. I think everybody can figure that out. So since Q is equal to K, it's at equilibrium. Now, I chose that on purpose, that we start off at equilibrium, and now we're going to mess it up by changing things. So we'll do a series of thought experiments where we go through and change the concentrations of individual components, or change the partial pressures of individual components. So we're going to start by doubling the partial pressure of hydrogen. So if you feed hydrogen into this reaction, you will double the partial pressure. It's possible to double that partial pressure of hydrogen just by adding twice as much hydrogen. So here is our expression. When we put the values in and we've doubled the concentration or the partial pressure of hydrogen, we will now get 1 squared over 1 times 2 cubed. 2 cubed, of course, comes out to 8, so 1 over 8 is 0.125. Well, in this case, Q is less than K. Since Q is less than K, the reaction will proceed to the right. The concentration of our reactants will decrease and the concentration of our products will increase. So by adding a product, it shifted the reaction to the right. Or I'm sorry, by adding a reactant, it shifted the reaction to the right. The lesson here is increasing the concentration or partial pressure of a component will shift the reaction in the opposite direction. So by adding hydrogen, it shifted the reaction to the right. If we had added ammonia, it would have shifted the reaction to the left. So that is our first lesson. Next, I want you to think about these 3 components, nitrogen, hydrogen, and ammonia, and think which one has the strongest intermolecular forces. I'll give you a second. All right, hopefully you came up with ammonia as having the strongest intermolecular forces. It is capable of hydrogen bonding, and as a consequence, we would fully expect it to have the highest boiling point. And that definitely is the case. Well, so one of the tricks that we can do is to remove some of that ammonia by cooling it off, by taking the gases that we produce and cooling it off, and the ammonia will turn into a liquid and we can extract it out. So let's do a thought experiment. So experiment number 2, we're going to decrease the partial pressure of ammonia by half. So again, we're going to go back to our initial conditions where everything was 1 atmosphere, but we're going to decrease the partial pressure of ammonia by half. So that number up on top is going to become 0.5. So we'll get 0.5 squared over 1 and 1 cubed. That gives us a value of Q that is equal to 0.25. And when we relate Q to K, well, Q, because since K was 1, Q is less than K, and again, the reaction will proceed to the right. So by removing ammonia, that shifted the reaction to the right. We will find that the concentration of our reactants, nitrogen and hydrogen, will decrease, and the concentration of our product will increase as it's going towards equilibrium. The lesson here is decreasing the concentration or the partial pressure of a component will shift the reaction in the direction of that component. So by removing ammonia, we shifted the reaction to the right. If we had removed hydrogen or nitrogen, we would have shifted the reaction to the left. For experiment 3. Here we're not going to change the amounts of nitrogen, hydrogen, or ammonia. We're simply going to change the volume of our container. So these are all gases, which means they are all compressible. So we could squeeze on that container to decrease the pressure of each, to increase the pressure of each by decreasing the volume by half, we would double the pressures of all of the components. So the pressure of the ammonia, the nitrogen, and the hydrogen would each be 2. Well, 2 squared over 2 times 2 cubed, that's going to be 4 up in the numerator, 16 down in the denominator. That comes out to 1/4. That's going to give us a value of Q that is equal to 0.25. Well, again, Q is less than K. Since Q is less than K, this reaction will proceed to the right. So we'll find that by decreasing the volume, we would cause this reaction to shift to the right. So the concentration of our reactants would decrease and the concentration of our products would increase. Now, here's the lesson. Decreasing the volume will shift the reaction in the direction of fewer moles of gas. Let's come back over here and look at the equation. We've got 1 mole of nitrogen and 3 moles of hydrogen, so that's 4 moles of gas on the reactant side of this equation. There are 2 moles of ammonia on the product side of this equation. So by decreasing the volume, it shifts the reaction to the side with 2 moles of gas rather than 4 moles of gas. Now, conversely, if we had increased the volume, you might expect the reaction to go to the left. Well, that's what we're going to do on the next slide. So here on the next slide, we are going to double the volume. By doubling the volume, we will cut all of the pressures in half. So we will have all of those pressures. So these will all become 0.5. Instead of going up to 2, they'll go down to 0.5. Well, 0.5 squared divided by 0.5 and also divided by 0.5 cubed, that's going to give us a value of 4. So if Q is equal to 4, now Q is greater than K. Well, if Q is greater than K, then the reaction will proceed to the left. This is the first one we've had where the reaction proceeded to the left. The concentration of our reactants will increase because the reaction is proceeding to the left, and the concentration of our products would decrease. The lesson here is if we increase the volume, increasing the volume will shift the reaction in the direction of the greater moles of gas. So again, we had 4 moles on the left, 2 moles on the right. By increasing the volume, it shifted the reaction to the left. Next, we want to increase the temperature because there are all types of situation where we might be interested in either increasing the temperature or decreasing the temperature. Now, this one's a little bit different, and we're going to think about it in a slightly different way. This is an exothermic reaction. You can tell because delta H is negative, and so it is an exothermic reaction. Well, one way you can think about exothermic reactions is that heat is a product of an exothermic reaction. Now, it's not literally a product, but this is an effective way of thinking about the reaction. So if heat is a product and we increase the temperature, that means that we are adding heat to this reaction. Well, by adding heat, we are adding a product. Now, you'll notice I put it in quotes because, again, heat is not literally a product, but we can think of it that way for purposes of Le Chatelier's principle. So by adding heat, we would shift the reaction back to the left. We would drive that reaction back to the left. The concentration of the reactants will increase, and the concentration of the products will decrease. So the lesson here is adding heat to an exothermic reaction will shift the reaction to the left, and removing heat would have the opposite effect. So if we had cooled this down, that would have shifted the reaction to the right. We're going to see the endothermic example of this a little bit later after I talk about the setup, the industrial setup for the Haber process. All right, so here I want to look at the industrial production of ammonia. When ammonia is produced on an industrial scale, this is a diagram of what that equipment would look like. So we take advantage of several of the things that we talked about when we were looking at how we can affect the position of the reaction, how we can shift the reaction either to the left or to the right. We're trying to shift this reaction to the right, so we're constantly feeding in nitrogen and hydrogen, pumping those into the reaction chamber. So by constantly adding more of the nitrogen and hydrogen, that will help to shift the reaction to the right. That gas is pumped through. We do have to heat that gas up to a high temperature, about 500 degrees Celsius, and run it over a catalyst. Interestingly, the reaction only occurs when it is at the catalyst. So all the reacting has to occur right here. Some of the nitrogen and hydrogen will get converted into ammonia, and so we'll have a combination of nitrogen, hydrogen, and ammonia that gets pumped out of this container and comes over to here. There is a refrigerating coil here and a heat exchanger here that will decrease the temperature of our hot gases that are coming out. That will start to condense some of the ammonia, which has the strongest intermolecular forces. It will condense that ammonia into a liquid. So you'll see the liquid ammonia droplets coming here. And then you have a tank of liquid ammonia that is being produced. And of course, you can open up that and fill up a tank car with it, or a pipeline, or whatever, to continue on to the rest of your chemical process. What's left over is a mixture of gases that's mostly nitrogen and hydrogen, although there will be some ammonia left, and that will be combined with fresh nitrogen and hydrogen to go through the process again. Typically, when companies, factories are doing this process, they will continuously run this 24 hours a day for weeks, months in a row. And they can go as long as the catalyst is still working, and then they can constantly produce ammonia. It is a very energy-intensive process, so this is not something that that people would do unless they had a good reason. And of course, the good reason is that you can use the ammonia to make fertilizer. Now, you may be wondering, how much of the stuff do they make? Well, this is among the most widely produced chemicals in the world, and there are many, many production facilities. This is a picture of a production facility in Wagaman, Louisiana. It's right along the Mississippi River, so they can have tank cars that can carry away their ammonia and byproducts. But you can see it is a massive industrial process. And this particular facility, I believe, cost the company $850 million to build. It is a big money business. And so a lot of throughput goes through these facilities. There are facilities like this in Texas and along the coast, and there are other facilities all around the world. Usually they try to get it close to places where natural gas is cheap. And that's why Louisiana and Texas are such advantageous places to build this. All right, so that is our industrial production of ammonia. So we want to look at another reaction. This is one that we do in the lab. We've got this cobalt hexahydrate. That cobalt hexahydrate has a pink color. It looks like this over here. So that is a pink color. And then here is chloride. And one of the things we do in the experiment is add chloride. By adding chloride, it'll shift the reaction to the right. And we can tell it shifts to the right because we get cobalt, this cobalt chloride complex ion. All right, and it is blue in color. Well, we will find that if we have a mixture of this, so we take cobalt chloride and dissolve it in water, we'll have a mixture of this, and it will contain some of the cobalt hexahydrate and some of the cobalt chloride complex ion. Some of it's pink, some of it's blue, and it gives us kind of a purple color. for that mixture, and that is at room temperature. If we take that reaction and heat it up, it will get more blue, meaning that the reaction is shifting to the right. So by adding heat, we shift that reaction to the right. If we take that same container, the same test tube, and put it into a beaker of ice water, we'll find that it shifts the reaction back to the left. So cooling this shifts the reaction back to the left. So here are our observations. Adding heat shifts the reaction to the right. Removing heat shifts the reaction to the left. So think about that for a second. Is this reaction going to be endothermic or exothermic? So I'm going to give you a second to think about that. All right, well, hopefully what you came up with is that it must be endothermic. So by if it is endothermic, adding heat is going to shift the reaction to the right. Removing heat is going to shift the reaction back to the left. All right, and our final thing that we want to look at is the effect of a catalyst. So adding a catalyst changes the mechanism of the reaction, and that by changing the mechanism, we're going to decrease the transition state energy. So the transition state energy is the energy at the top of this curve. This is the uncatalyzed reaction, and here is the energy, this transition state energy of the catalyzed reaction. So by adding a catalyst, it will change that transition state energy. Well, doing that is going to decrease the activation energy, but it'll decrease the activation energy for both the forward reaction and the reverse reaction. So we'll find that both the forward and the reverse reactions will go faster. As a consequence, we'll find that it does not change the position of equilibrium. Equilibrium is achieved faster, but the position of equilibrium is unaffected. So adding a catalyst does not affect the position of equilibrium. So now we want to look at the last problems in chapter 15, and I'm sure you're all excited about this, that we're almost done here with chapter 15. So we're going to switch over to the in-class assignment and do 51 and 53. All right, so consider the following equilibrium for which delta H is less than 0. We want to see how each of these will affect an equilibrium mixture of the three gases. All right, so since delta H is less than 0, that means it is exothermic. So I'm going to put here plus heat. So plus heat. So it's exothermic, so heat is a product. So A, O2 is added to the system. Well, by adding O2, we are adding a reactant. When we add a component, the reaction will shift in the opposite direction. So adding O2, the reaction will shift to the right. So shift to the right. If the reaction mixture is heated, well, by adding heat, we're adding a product. And again, I'm going to put that in quotes. It's not literally a product, but we're adding the product of heat. And by doing that, we will shift the reaction back to the left. Next, we'll look at the volume of the reaction vessel is doubled. So when we increase the volume of our vessel, by increasing the volume, it will shift the reaction to the side with more moles of gas. We have 3 moles of gas on the left, 2 moles of gas on the right, so this will shift to the left. All right, D, a catalyst is added to the mixture. Now, as we just saw, the effect of a catalyst is that it gets to equilibrium faster, but it does not affect the position of equilibrium. So, how will it affect? It will no change. If it was already at equilibrium, there will be no change. Next, the total pressure of the system is increased by adding a noble gas. Well, we could look at this and say, well, Kp is equal to the partial pressure of SO3 squared over the partial pressure of SO2 squared times the partial pressure of O2. Well, what happens to these partial pressures if we add a noble gas is that they are not going to change. And since the partial pressures will not change, our equilibrium position will also not change. So here we're going to put no change. And then finally here we've got SO3 is removed from the system. By removing SO3, we are removing a product. Remember, when we remove something, it will shift the reaction in that direction. So here, this will shift to the right. All right, and now for our final problem, number 53. How do the following changes affect the value of the equilibrium constant? And it's important here that we're talking about the equilibrium constant for a gas phase exothermic reaction. Well, I'm here to tell you that just like with the rate constant, the only thing that will change the equilibrium constant is the temperature. So all of these things that are not temperature are going to have no effect. Removal of a reactant or product, no change in K. Decrease the volume, no change in K. Decrease the temperature, there will be a change in K. Let's look at that in a moment. And then addition of a catalyst, no change in K. So let's come back to this. The gas phase exothermic reaction. We don't know what the details of this are, but we do know that we've got something that's in the gas phase. So I'm going to come down here. We've got something that's in the gas phase. So this is in the gas phase, and it is in equilibrium with something else that is also in the gas phase. And since it is exothermic, we'll say plus heat. Well, decreasing the temperature, what direction would that shift the reaction? So by decreasing the temperature, we would be removing heat. By removing heat, the reaction would shift to the right. So our reaction would shift to the right. Well, in shifting to the right, we need to remember that it was not the reaction ratio or the reaction quotient that changed here. What changed was the equilibrium constant. And the thing that shifts our reaction to the left is when Q is less than K. Well, when Q is less than K, and it wasn't Q that changed, it was K that changed, that means that our equilibrium constant will increase. So again, the reaction shifts to the right because we removed heat by decreasing the temperature and removing heat. Since it's shifting to the right, that means Q is less than K. Well, we didn't actually change any of the components of the mixture, so Q didn't change. It was only K that changed. Since it was K that changed, that means that K must have increased. So K will increase when we decrease the temperature. Well, that is, let me go back here. That, I believe, yes, that is the end of chapter 15. And that also represents the end of the content for the second exam.